Okay, so for the last quiz we had this quadratic form, and you had to diagonalize it or make it without cross terms, and that meant that you had to calculate a matrix P that gives the substitution, and then also say what the new form was. Okay, so that's what I expected from you was the following. So first of all, of course, we have to find the matrix, the symmetric matrix that is associated to this. So it's a symmetric matrix. And I hope that's, of course, if you do wrong, then everything else is wrong. We look at what these terms are. Again, one more time, in case you find this hard to imagine where everything goes, just label everything. And then you see each spot here corresponds to x1 times x2. But there's always a symmetric spot that corresponds to x1, x2. So for instance, that's why this -2 has to go there, but we have to split it evenly. So we -1, -1. This is x1 squared, that would go there. This x1, x3, we have a coefficient -2, so again we split it evenly, -1, -1. The 2 is for x2, x2, this 2 for x2, x3, x3, so we have zeros here. So that was the matrix. Step 2 was then the characteristic equation. It's symmetric, right? So the characteristic equation would be, well, we have to subtract lambda from the diagonal. Now you have the choice, either you expand it along a column of a row, or you do some row operations. Let's expand it perhaps, just to show you that you can do this. I'm going to expand along row 3. Because at least I take a row with at least 1 0 in. So with expansion, you always have to be careful here. We have plus, minus, plus, minus, plus, minus, right? So we know exactly what the signs are. Okay, so the first factor here, -1. And then we scratch this out, and we see we get -1, -1, 2 minus lambda 0. Okay, let me get rid of these guys again. And then we have plus, again a plus, right? It's plus here, 2 minus lambda, and then we scratch out, we get 1 minus lambda, -1, -1, 2 minus lambda. Okay, we work this out. This is -1, 0, minus, minus, so plus 2 minus lambda, plus 2 minus lambda, 1 minus lambda times 2 minus lambda, minus, 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 -1. Okay? So that is, with this minus here, so we get minus, look, I'm going to do something that you might not have done, but it's not hard, this one, but to just show you that sometimes you have to look for things. So, okay, let's expand this at least. That's a 2, minus 2 lambda, minus lambda, plus lambda square, -1. Okay, right. So, sorry, there's a parenthesis here. Now look, you have a 2 minus lambda here and a 2 minus lambda there. You need to factor this thing. Now, if you expand it, it's also not hard. But I'm just showing you, you can sometimes save yourself and say, okay, I have this 2 minus lambda, let's factor it out. And what I'm left, a -1 there, and there I'm left, well, the 2 and the -1, they combine to a single 1 here, right? So I get -1, and then what is left here is 1, combine this as 3 minus lambda, plus lambda square. And the -1 with that 1 cancel, and we get 2 minus lambda, minus 3 lambda, plus lambda square. Now, don't make a mistake to expand this. Never expand when you're trying to factor. If you're completely factor, of course, we expand it here because we're still a sum here. Okay, but here not. So we have 2 minus lambda. Then there's also a lambda that I can put out in front, and then I have -3 plus lambda left. And from that I can see what the roots are. 2 minus lambda equals 0 means that lambda is 2. This means lambda is 0, and this lambda is 3. So we have 3 eigenvalues, and in fact, this means already that I know what the quadratic form will be. So the quadratic form will be, this will be the coefficient of the quadratic form, 2 times y1 square plus 0 times y2 square plus 3 times y2 square. Now, there's a choice in which order you take these eigenvalues, and therefore there's a choice in which order these variables come. So this is not the only solution, right? You could also have put first 0, then 2, and then 3, and then you would have a form with no y1 square, but with a 2y2 square. Okay, so it doesn't mean if you don't have this that it was a wrong question. That means that you made a mistake. It's just a choice that you make. But okay, so this is not enough, right? Because what I need is to see is the matrix P. And so for that, we need to do all this calculation that we're going to do now. So step, I don't know, 3, I guess, the eigenspaces. So let's do the eigenspace for lambda. Now, I have to be careful, right? If I decide that this is going to be, I set a 3, but I wrote a 2 here, sorry. Right? Lambda 2, lambda 0, no, y2, lambda 3, that is 3 times y3 squared. But I'll say it again at the end. But I should keep the same order that I did, because otherwise I get a different matrix. Okay, lambda is 2. So my matrix, I'm going to keep writing it here. It's my matrix was 1, minus 1, minus 1, minus 1, 2, 0, minus 1, 0, 2. So I'm now subtracting 2 from it, so minus 2, minus 2, minus 2. So the matrix that I get here, that of which I have to count the eigenspace, the null space, is minus 1, minus 1, minus 1, minus 1, 0, 0, minus 1, 0, 0. Okay, except for the negative 1, that's a bit annoying, so let's get rid of that. Minus 1. I get 1, 1, 1, minus 1, 0, 0, minus 1, 0, 0. Okay, we do row 2 plus row 1, and row 3, I should have made it a little bit lower, I guess. Row 3 plus row 1. So we get 1, 1, 1, 0, 1, 1, 0, 1, 1. So one more thing to do here is row 3 minus row 2 to get this 0. We get 1, 1, 1, 0, 1, 1, 0, 0, 0. Okay, that's the echelon form. We see that we have one free variable, so we know we are on good track, but we need, since we are looking for an eigenspace, which is a type of null space, means it's a type of solving a system of equations, we have to go to the reduced echelon form. Please don't forget that. Don't try to solve this by hand, because then you get completely confused about what is free and what is pivot variable. So go all the way. So this means I need a 0 here. So this is row 1 minus row 2, using the pivot below it. Okay, so I get 1. So I'm multiplying this with negative 1 added up there, so 0, 0, then 0, 1, 1, and then 0 I don't write anymore. So we see that this is a pivot variable, x1, x2 is a pivot variable, so x3 is a free variable. And so now I can write x1, x2, x3. I know already that x3 is equal to x3. Perhaps sometimes it's best to write it first, because otherwise you get confused, because weird things might happen. Like for instance here, what is this it tells me? Well, it tells me that x1 is 0. There's no x3 here. But here we get minus x3. So we get x3, 0, minus 1, 1. Okay, so I explain one more time where this come from. Well, this means that we have 0 times x1, x2 plus x3 equals 0, right? These are the coefficients of this equation. And so if we solve for x2 here, we see that x2 is equal to negative x3. That's why I write negative x3 there. Okay, so I factor out x3, and we need to normalize. So we take the norm of this fellow, and that is the square root of 1 plus 1, that is square root of 2. So our orthogonal basis is 0 minus 1 over radical 2, 1 over radical 2. Okay, that's for lambda equals 2. Then next one was lambda equals 0. As I said, you can choose your own order, but you get slightly different answer. So now the matrix was I'm just going to copy it. It's just, if you don't believe me, here it was, right? Okay. Okay, we have a pivot here, so we do row 2 plus row 1, and row 3 plus row 1. Get 1, minus 1, 0, 1, negative 1. And you apply that 0, negative 1, 1. Okay. That's good news here. I see already what's going to happen. Row 3 plus row 2. 1, minus 1, 0, 1, negative 1, and this is going to be 0, 0, 0. Okay, so we have our two pivots, but above this last one I need a 0, so I have to do one more thing. Using this row, where now we're going from bottom to top, so we do row 1 is row 1 minus 2, no, not minus, plus row 2. That is 1, so I'm adding that is a 0, I'm adding that's negative 2. 0, 1, negative 1, 0, 0, 0. No, I shouldn't write the last one. Okay, so what x1, x2 are pivot variables, x3 is a free variable. So x3 is equal to itself, and then these are equations. This first equation tells me that x1 is equal to 2 times x3, and the next one tells me that x2 is equal to x3. So we get x3, 2, 1, 1. And the norm of this thing, right, we have to normalize. That is 4 plus 1 plus 1, that is radical 6. So the basis here, I'll write it here, is 2 over radical 6, 1 over radical 6, 1 over radical 6. Good, and then the last one was lambda equals 3, if I'm not mistaken. Yeah, lambda equals 3. So our original matrix was, well, I see it over there, right? This was the original matrix. So from that, I'm now going to have to subtract 3 from the diagonal. So minus 2, minus 1, minus 1, minus 1, minus 1, 0, minus 1, 0, minus 1. Okay. I don't want fractions, so I'm going to swap around. No. All right, let's do it the long way. Swap around the first two. So I get minus 1, minus 1, 0, minus 2, minus 1, minus 1, minus 1, 0, minus 1. You could have already changed the sign too, but as I said, if you mix things, it's sometimes dangerous. So let's take the extra step here. So now we have a 1. The other ones, I don't care what they are, because I'm going to get rid of them. Row 2 plus 2 times row 1, row 3 plus row 1. You get 1, 1, 0. So I'm multiplying this with 2 and add up, that's 0. 2 minus 1 is 1, 0 is minus 1. And then I'm just adding these things, 0, 1, negative 1. Great, because this tells me that the last row is going to go. Row 3 minus row 2. 1, 1, 0, 0, 1, negative 1, 0, 0, 0. Now I have my pivots, but again, this one here has to go. So we have to do row 1 minus, this one has to go, right? Row 1 minus row 2. I'm using row 2 because that's the pivot that I'm going to use. And that is, so I'm multiplying this with negative 1 and add up. So 1, 0, minus minus is plus 1, 0, 1, minus 1, and the rest is 0. Okay? So x1, x2 pivots, x3 is the free variable. This means that x3 is equal to itself. The first equation tells me that x1 is minus x3, and the other one that x2 is equal to x3. So x3 minus 1, 1, 1. We normalize. Minus 1, 1, 1. That's radical 1 plus 1 plus 1 radical 3. So I told you, right, that you cannot expect that all these vectors are going to have the same norm. You see, you have really different ones, radical 3, radical 2, radical 6 we had. So the basis is minus 1 over radical 3, 1 over radical 3, 1 over radical 3. Okay, and so we can now write down the answer, right? Step, I forget, lost count a little bit, step 4 or step 5. Step 4. I thought there were 5 steps, but for some reason I'm only at step 5. Okay, so what is P and what is D? Okay, we already decided that we're going to take the order 2, 0, 3, the 3 eigenvalues, right? So and then that means that P has to be the 3 basis vectors in that order. For 2, we had the basis vector, where is it? This guy, 0, minus 1, radical 2, 1 over radical 2. Then for 0, our basis vector was this guy, 2 radical 6, 1 radical 6, 1 radical 6. And then the last one is here, minus 1 radical 3, 1 radical 3, 1 radical 3. So this means that if we change the variables, the x variables, into so this is P, this is just a matrix, right? I make this, I don't know, I make my script P's, my capital P's always with a little bar underneath. I don't know whether that confuses you, we don't need to say that's a vector. But here we have a vector, the vector of the variables, and this is a new vector, and if we do that, then we know that the new quadratic equation, I'll write it up one more time, but you don't have to do this, right? You can write it down right away, because we know what happens with diagonal matrices. It's 2 times y1 square plus 0 times 2y2 square plus 3 times y3 square. Okay, so, but I needed to see the matrix P, and I needed to see this. And that's it, right? So, by the way, it's not part of the question anymore, but I could have done, suppose if I would calculate d square, it's not the best, not d square, sorry, a square, the original matrix a square. Remember, we have done questions like that. I'm just saying now we have the fact that it's orthogonal makes it easier. But that was one of the quizzes. I don't know why I said this. Ignore this. Okay.